Hi, everybody. It's Professor Mitchell. We are starting a new chapter today, Chapter 4, on Introduction to Probability. So you can see this is a pretty short chapter, only 3 sections. So we will start with section 4.1, an Introduction to Probability. A probability is a numerical value ranging from 0 to 1. Probability indicates the chance or likelihood of a specific event occurring. If there is no chance of the event occurring, the probability is 0. And if the event is absolutely going to occur, if it's certain to occur, guaranteed, the probability of it occurring is 1. So most interesting examples fall somewhere in between. All right, so it's not uncommon when we start a new chapter to start with a lot of vocabulary. So this would be one example. When we talk about an experiment in probability, that's the process of measuring or observing an activity for the purpose of collecting data. So one example would be rolling a single 6-sided die. When we talk about the sample space for an experiment, we're talking about all the possible outcomes or results of the experiment. So the sample space for the single die experiment is the numbers 1 through 6. 1, 2, 3, 4, 6. An event is one or more outcomes of an experiment. So sometimes we say it is a subset of the sample space. The outcome or outcomes is a subset of the sample space. I didn't read ahead. An example of an event would be rolling a pair with 2 dice. Or if we wanted to stick with the single die example, we could say rolling an even number would be an example of an event. A simple event is an event with a single outcome in its most basic form that cannot be simplified. So an example of that would be rolling a 5. All right, if you can identify one specific outcome from your sample space that represents that event, that makes that a simple event. All right, here are some more examples of experiments and their sample spaces. When you flip a coin, the result is either heads or tails. When you answer a multiple choice question, of course, this depends on how many choices there are. There are not always 5. The sample space could be the letters A through E if there are 5 choices. If you're inspecting a product to determine whether it's defective or not, the sample space would just be defective or not defective. And if you draw a card from a standard deck of cards, the sample space would consist of the 52 cards in the deck. So there would be 52 elements in that sample space. All right, there are 3 methods for assigning probability. There's the classical method, the empirical method, and then the subjective method. So we're going to talk about all 3 of those, starting with the classical method. The classical method is used when the number of possible outcomes of the event of interest is known. And in a math class that covers probability, this is the kind we talk about the most. The formula for classical probability, notice that probability is written P of A. So P for probability, and then A is the name of the event. So that would be the number of possible outcomes that constitute event A divided by the total number of possible outcomes in the sample space. So here's an example. The experiment is to roll a die once. So again, the sample space is 1, 2, 3, 4, 5, 6. If we define event A as rolling a 5, there are 6 possible outcomes in the sample space, but only one way of rolling a 5. So the probability of event A would be 1/6, which can also be written as 0.167. That's rounded to the nearest thousandth. Sometimes probabilities are written as percentages. Now, if you're doing online homework, you have to pay attention to the form of the answer that they want. It's been my experience that they usually want either a fraction or a decimal not necessarily a percentage, but just make sure you read the directions. This is an example of a simple probability. It represents the likelihood of a simple event, right? Simple event because it only contains one outcome. All right. If the experiment is to roll a die once and the sample space is the numbers 1 through 6, the classical probability, this is very, very important, assumes that each event in the sample space has the same likelihood of occurring. So most of the time when you roll a die, that's true, that any of those numbers 1 through 6 are equally likely to come up. I think they do make, trick dice that are weighted somehow so that certain numbers are more likely to occur than others. So you just want to make sure you're not using one of those. The set of events is collectively exhaustive if the sample space includes every possible simple event that can occur. All right, that brings us to the empirical method of assigning probability. So this is where you actually do the experiment a whole bunch of times and count how many times the event of interest actually occurs. So the formula for that is probability of A equals the frequency at which event A occurs divided by the total number of observations. All right, so here's an example of where you would use empirical probability. A survey of 400 new graduates were asked how much they owed in student loans. The results are shown in this table. So the first question is, what is the probability that a randomly selected graduate has between $5,000 and $9,999 in student loans? And the second question is, what is the probability that a randomly selected graduate has $20,000 or more in student loans? So while we're here, let's just notice that there are 102 graduates that have this amount of student loans. Now, the second question, 20,000 or more, consists of two groups, doesn't it? So here are 66 graduates that owe basically between 20 and 30,000, and another 47 graduates that owe 30,000 or more. All right, so those two groups add up to what, 113. So let's hold on to those numbers, 102 and 113. Oh, good, they put this table on the next slide. I was afraid they might not have. So the probability that a randomly selected graduate has between $5,000 and $9,999 in student loans is the 102 observed people that had that amount divided by the 400 people that were observed. So as a decimal, that comes out to 0.255. And then the probability that, excuse me, a randomly selected graduate has 20,000 or more in student loans would be 66 plus 47. That amount divided by 400, which comes out to about, actually, I think exactly 0.2825. Now, the law of large numbers talks about the relationship between a classical probability and an empirical probability. And what it says, and this is a really, really powerful thing, it states that when an experiment is conducted a large number of times, the empirical probabilities of the process will converge to the classical probabilities. They will get closer and closer to the probability that's predicted by the first formula that we looked at. So a very simple example of that would be if you flip a coin a large number of times, think like 1,000 times, the observed number of heads should be very close to 50%. I doubt it would be exactly 50%. It's unlikely that you would get heads exactly 500 times, but it's very likely that it would be close. All right. Now compare that to if you flip the coin only, let's say 6 times, really could be anything. All right, I guess 3 would be the most likely outcome, but it could easily be something else. So the law of large numbers says repeat your experiment a whole bunch of times, and then the observed probability should be very close to the classical probability. All right, and that brings us to subjective probability. This is what you do kind of as a last resort. This is used when classical and empirical probabilities are not available. So instead, you can use experience or intuition to estimate the probability. So as an example, they say the probability that inflation will be greater than 4% next year. All right, nobody's a fortune teller, right? We have no way of either calculating that or measuring that because it's in the future. So, you know, you would either just guess or maybe study, you know, some historical trends to see, you know, look for other years that were similar to this year and see how many of those had inflation greater than 4%. All right, and then we have basic properties of probability. We're going to be using these quite a bit throughout this chapter. And I think most of these we've already stated, right? If the probability of A is equal to 1, then with certainty, event A must occur. On the other hand, if the probability of A equals 0, then with certainty, event A will not occur. The probability of any event must range from 0 to 1. Remember that. So when you're calculating a probability, if you get an answer like 2 or -1/2, that's definitely not correct. Okay? It has to be between 0 and 1. And this one is very important. The sum of all the probabilities for the simple events in the sample space must be equal to 1. Right? Those probabilities have to add up to 1. All right, this one we will be using quite a bit in this chapter. The complement to event A is defined as all of the outcomes in the sample space that are not part of event A. And your textbook denotes the complement like this, A with a little apostrophe on it. That in math, that symbol is read prime, A prime. So the formula for the complement rule is that the probability of A plus the probability of A complement has to equal 1. All right, now that kind of makes sense when you think about rule number 4. The sum of all the probabilities for the simple events in the sample space must be equal to 1. Now, all of those simple events are either going to be part of event A or they're not going to be part of event A. So if you were to list all your simple events in this Venn diagram, some of them would fall here and the rest of them would fall out here. So it makes sense that those two events, the probabilities should add up to 1. Now the form that we actually use the complement rule in looks like this. It says the probability of A is equal to 1 minus the probability of A complement. And where we use that is when we're trying to calculate the probability of an event. Sometimes that probability is difficult to calculate directly. So we'll think about the complement of that event. Is it easier to find the probability of the complement? And if it is, then we'll do it that way. We'll find the probability of the complement and subtract it from 1. And that is the end of section 4.1. So we'll see you next time for 4.2.